previous video is that Taylor's theorem basically said that there's some value between where we're approximating, some value c, between where we're approximating, which is the point x equals whatever happens to be, and then our center, which is our value of a. There's some value in between c, in which if we evaluate the next derivative of our function over that n plus 1 factorial times the x minus a to the n plus 1th power, then we're going to get the exact remainder. Right? Now the problem with that is we don't know what that value of c, that exact value of c happens to be. And if we did, then this whole thing would be pointless anyways, because we could get the exact error. We're just trying to find a bound on an error. How far off are we? All right. So we have now the Lagrange form of the error. All right, and that's what you see, the Lagrange error bound. They may reference this by name on the exam. They may not. They may use that absolute value of f of x minus t of x or p of x to talk about the error bound. If we're going to go with the Lagrange, here's the deal. Since this is very cloudy right here, what we've come up with is that this expression is actually less than or equal to almost the identical expression, except you've got this capital M here. Right? What is M? M is the maximum value of the next derivative. All right? Since we can't find the exact c to plug into our next derivative, let's just get that next derivative and see if we have a maximum value of that derivative, and then we can use that number, and our error will be less than or equal to whatever this expression turns out to be once we plug in that maximum value of the next derivative. What am I saying by all this? Let's put it into example 29. Right? With example 29, we're revisiting it. We know that f of x equal to sine of x. Okay, so our Taylor function, our Taylor series goes on forever, but we're interested in just the 5th degree Taylor polynomial. So those are the first 3 terms right there. Okay, if we were to approximate the Taylor polynomial at 0.2, that means we're going to place all 3 x's with 0.2s, and we'll calculate that. And I feel free to pause the video at this point and come up with the calculation. Hopefully you'll get the same thing that I did, which is 0.198669, and then it starts repeating after that. Okay, so that's the value that we came up with. That's an approximation for the sine of 0.2. All right, notice we have the approximation symbol. All right, what's the exact value? Well, if you do that on your calculator, you'll see here in orange that my calculator has popped out a very similar number, except that we have the 0.8 after the first 2 3s. So there is a difference. We're going to talk about that difference more in a second. Okay. What's the maximum difference that it could be? That's the Lagrange error bound. So what Lagrange says is, in order to get that error, we're going to go to the next derivative. Now this is the 5th degree, so we have to go to the next value of n, which would be 6. So n is 5. We add 1 to that, we have 6, which is why you see the 6 factorial here. And you also see the exponent of 6. Okay. We have to fill in the other stuff. Right. Now, the series for sine is centered at 0, so we can replace a with 0. And the value of x is the value that we are approximating at, which is at 0.2. So we can put 0.2 in right there. Okay. Now we need this m. Now m is going to be the maximum value of the next derivative. We've already worked through our derivatives for sine. All right, we know that f of x is sine x, and we know that f prime is cosine, and f double prime is the opposite of sine, and f triple prime is the opposite of cosine, and then the 4th derivative sends us back to sine. So our 5th derivative, all right, we're looking at a 5th derivative of cosine, all right, and our 6th derivative would be equal to the derivative of cosine, which would be the opposite of sine x. Now think about the opposite of sine x for a minute. All right, it's just the sine function reflected over the x-axis. All right, but it doesn't really matter whether or not it's reflected, whether it's sine x or the opposite of sine x. What's the maximum value of sine x, or the maximum value of the opposite of sine x? Yeah, it's 1. Okay, look at the graph again if you're not sure. Notice that the graph is always between 1 and -1. So the maximum possible value of the 6th derivative is going to be 1. We can't get any higher than that. let's use 1 for our m. All right, that's where we're going with all this. We can use 1 because we can talk about our sixth derivative. And that's the shortcut that the exam writers will use, where they'll tell you what the maximum value of the next derivative is going to be. All right, and you'll see that in a future example where they punch in that number for you. You just have to take care of the dividing by the n plus 1 factorial and having it to the n plus 1 power. So where are we going with all this? Well, now let's figure out this value. If you take your calculators out and you punch all this in, let me grab my calculator. I have a value of, here we go. This is equal to 1, 2, 3, 4, 5, 6, 7, 8, repeating. Okay, that is the Lagrange error bound, which basically says that at most, this is how much we're going to be off by. Okay. Well, that's our answer. That's our Lagrange error bound. All right, we found the most that we're going to be off of. We can actually see in this case what our actual difference was. If I told you to hold that thought for a second, if you now do the original approximation minus the actual value, I think we come up with 0.1, 2, 3, 4, 5, 6, 7, 8, 2, 5. So you can see that we actually have a number in purple, which is our actual area, and it's smaller than the maximum area that we might have, which should be the case. The maximum area should be the most that we're off by. We're actually off by less than that, but the most that we'd be off of is by that value right there. So that's the idea with these questions is, can you find the maximum amount of error that we're going to have? Now, the actual error will probably be much less. We're just trying to find the maximum error. That's your Lagrange.